And the first talk will be given by Tanja Lange, who's done a lot of work in code-based constructions. And she will tell us, she will explain us assumptions underlying code-based crypto.
Thank you. So this is a little bit of a merged talk from the things which were announced initially for Alex, Mai, and myself. So I hope we didn't compress it down too far. So we have seen codes already coming up a few times, also in bounding distance decoding and so on. And I was thinking of even leaving some of the pictures that Daniele drew, because the pictures we draw for code-based crypto are very similar to the pictures that we draw for lattice-based cryptography. Now, one difference is, and I'm only going to cover binary codes today, is that for us everything is discrete. There are no Gaussians running around. There is no a little bit away from it. It's either this or that, 0 or 1. And so we're looking often at parity check matrices, and so one of the representations of our codes, or one of the ways to define whether something is in the code, is by saying, does it satisfy a certain number of checks? So here's a very easy example of a Hamming code. Our code word's going to be strings, in this case of length 7, so there are 7 positions here. And if you have something which gets transmitted without being exposed to any noise, then the string of 7 positions will satisfy all these 3 check equations. So just to say what we mean by this, it's basically a vector times matrix multiplication. I'm thinking of my vectors as column vectors, but that messes up the slides. So if I need to write them out, it's a horizontal thing, but then I don't want to put transposers anywhere. So please forgive me for not putting t's everywhere and 90-degree flip your vectors as appropriate. So this thing would normally be a vertical thingy. Okay, so then this first line is just we're adding the first 2, not the third, and then so then this position and this position, we always start counting in 0, and so we're getting this nice scheme matching the matrix. And if you find any error somewhere, like if one of the bits will flip, then at least one of these equations will not hold. So I promised to you it was only one bit that got flipped, and we're seeing that the first equation doesn't hold, the second does, and the third doesn't. So we have an error pattern, or we will call this syndrome of 1, 0, 1. And so, okay, it's just 7 positions, so you can run through them and test all of them, or you can also just look, because I wrote them in kind of a obvious representation. So if the first and the second, the first and the third are wrong, the second one is fine, then I guess you're looking into this position, and yes, indeed, B1 is the one that got flipped. And of course, if it was more errors, if you have 2 positions that are wrong, you could, for instance, have that the B6 is wrong and B4 is wrong, you would see the same pattern. But we always assume that fewer errors are more likely. So if one error gives this pattern, then we assume this one error happened. Now, of course, we're looking at much, much bigger matrices, but then they don't fit on the slide and it all gets kind of messy. So I wanted to give one nice example here. Also need to fix some notation. So the length is normally called n, so that's just how many bits are in our code word. We distinguish between words that are in the code, so that satisfy these parity check equations, and things which arrive, so that have gotten an error after. So there I will try to say vector or received word, because this is the code word plus some extra e. So algebraically, we just added something, well, 0, 1, 0, 0, 0 in our example. And then this matrix, well, it gives you a number of equations. So it kind of restricts how many of those 2 to the n words are actual code words. And so in the case that we have full rank, if you have n minus k equations, you're getting a code of dimension k. That means there are 2 to the k words that satisfy it, because we have n minus k restrictions. Yes, this sounds a little artificial. Why don't I say I have k restrictions? That's just historically coming from coding theory, that we give a nice name to the dimension, and then the number of equations has to deal with a minus in it. Also in cryptography, when we're dealing with these codes, with these matrices, because those are going to be our public keys in the end, there's some redundancy in them. We can add those rows and do Gaussian elimination on those, and we're getting the same restrictions. So we often like to restrict them such that, represent them such that the end of this is an identity matrix. Now, that doesn't always work, but since it's nice for compactifying, you basically, in this example, it looks like you're saving half, and if you have more extreme choices between your n minus k and your n, you might actually save a lot more or a lot less. And so we like to put them into what we call systematic form, which means there's an identity matrix on the right, and if you're reading other books, it's on the left, but well, okay, somewhere. And then we ignore this and tell our crypto system, well, you implicitly know that there is just this extra matrix. Now, coding theory has been studied for, I put here 65 years, I could probably put a few extra, so around 70 years of coding theory. The main target was finding nice codes, where nice codes means codes which we can efficiently decode. If somebody sends us this x plus e, or this received word, which is not the real thing, how can we efficiently figure out where the errors were, and then correct the errors, get the word back? But there also are some theoretical results which say, well, you can't just hope that this always works. So if you have a random code, then there's a result that even deciding whether there is a code word, getting a vector and deciding whether there is a code word in a given distance, that is NP-hard. Now, of course, we know that NP-hardness doesn't really mean anything for cryptography, but this is still in the world of coding theory, what coding theorists have done, finding nice codes, but also figuring out results. Yes, question?
I guess you mean not random code, but for worst case codes. Huh?
Sorry, yes. The typical statement is that if you have a code which doesn't have any structure, if you have any of those nice codes, then you are definitely in an area where you have efficient decoding. And so then the what they proved is a worst case statement that is correct, and we believe that this holds for random codes. And then when McLeish came up with his crypto system back in the 70s, it's fairly early, he noticed that there is a distinction between the random case or the worst case. You're right, it's worst case result, but there are I think there are some results on average cases as well, but I'm out of my depth, so I don't know. So what McLeish is saying is use this distinction between nice codes that we have and random codes to build a crypto system out of it. Now, I'm going to show you not the original McLeish system, I'm going to show you the version of Niederreiter, which is fitting into the system of parity check matrices. The one thing which is nasty about Niederreiter is that it's not as easy to understand how you encrypt messages, but nowadays we don't want to encrypt messages, we're doing a hybrid encryption, so where we're just encrypting random strings, which we want to use for symmetric crypto, so that is easier. But historically, what McLeish saw was this, there is a complexity difference between those two, and my computer tells me I'm speaking too slowly, so let's go for the next slide. That wasn't me. Okay, so 78 McLeish. So to put this in perspective, 76 was just Diffie and Hellman, 77 was RSA. So this is really in the early days of public key cryptography where people toying around with, hey, what is my favorite hardness assumption? What is my area of research, number theory, coding theory, whatever? And can we build something? Surprisingly enough, this McLeish paper just got published as a technical report and never made it into any other literature. We don't really have much details. It's just a very short paper. He doesn't really justify his choices. He picks a very particular code family due to Goppa, which, okay, was very fashionable at that point, had come out just a few years earlier. But he doesn't really say why he picks these codes. It is one of those mysteries that I still have, is figuring out, like, did he try others and could break it, or did he just like this one? I mean, Goppa codes are nice, they're efficiently decodable. There are also many of those codes, that's also a nice feature of them, but that still doesn't justify picking them over some others which turned out to be pretty broken. Now, he posts some parameters, and in his paper he says this is for 2 to the 64 security. And that's one of the things that I find very remarkable of the McLeish system, is that the predictions of the hardness have held up really, really well over many, many years of work. It felt a little bit cruel to break a 30-year-old crypto system and go like, "Buff, we got you." Because, I mean, 30 years later, you have a ton more computational speed. I mean, 2008, when we finally, with a few friends, put together some clusters and broke those parameters, it was not by smartness, it was mostly by advances in computing that we could broke it. And okay, there were 2 to the 60 cycles, not 2 to the 64, but it's very close. If you look at like the initial parameters for RSA, they were missing a lot of big complexity steps that happened. And with McLeese, his parameter choices were pretty good and have held up well. If you look at what he had known as in what attacks do we have that decode generic codes, there was a 1962 paper by Prange. I'll get to that a bit later for the details. And that was basically what was guiding his analysis of how long it should take to break this. And when you look at the main constants, so if you want to have something which has L bits of security, so takes 2 to the L to break, then the the key size grows with the main constant here and then has some lower order terms in the little o of 1 here. And this C0 back for the Prange attack is 0.74 something. Okay, so that tells you how you choose your keys, and then, well, okay, you can still lose a few bits of security. Of course, the O of 1 matters a lot when you're making concrete choices, but it's interesting to see how the scaling works. And then comes a whole bunch of security analysis. So even though it was just a technical report, coding theorists liked the system and went ahead and were like, hey, well, now that you have a concrete target, how can we do this more efficiently? I mean, for complexity theory, once you know it's exponential time, you kind of stop caring. But if it's a crypto system, you want to know what is this exponent. How long does it take? Can I shave off a little bit? Even if I can shave off constants or little o of 1 pieces, it's a lot. And so there's a bunch of analysis. Some I put post-quantum, so those are considering quantum cryptanalysis of these systems. It is the minority, on the other hand. Well, it helps to have a whole bunch of literature developed to then turn into quantum algorithms. So Dan's initial paper there is taking basically the Prange algorithm, and then Kashiga Tillich and Elena are taking the more advanced algorithms that happened afterwards. From a historical perspective, I find it very interesting that all of this work, 40 years of work, quite a few papers, or if I take Prange into account, I can even claim it's more than that, but let's say 40 years, it's almost 60. The constant in this key size estimate, the main constant, not the little o of 1, there was lots of changes in little o of 1, but the constant is the same 0.74. So there have been a lot of work, there have been analysis, all of those papers totally deserve to be published, and there are some which have changes in little o of 1, that some which are just like optimizing in smaller notions. I mean, when we did the actual cryptanalysis, when we put the computers to work, we optimized every constant we could, no question. But it didn't do much harm on the asymptotics. So if you want to achieve pre-quantum security or post-quantum security of certain sizes, then, okay, we basically know what to do, but you also now understand why the system is not quite as popular as RSA. These numbers are a little bit large. So if you can have RSA, which for pre-quantum security gives you, say, 128 bits, and you're in this range, you're just dealing with 3072 bits. And this is a quarter of a megabyte. There's a big difference here. And the main difference, or the reason why the keys are so big, is that we're dealing with these matrices. So there is this lambda square. So if you want to increase the lambda, if you want to increase the security level, we're increasing it in both directions. We're increasing it in the n direction and in the n minus k direction. And so we get a quadratic growth, and that means that the keys are inconveniently big. On the other hand, if you have a system where you basically give your public key to somebody once, and you really trust this public key because, well, has gotten 40 years of cryptanalysis, it doesn't really matter how big this key is. I mean, a megabyte of storage on your hard disk is close to nothing. And even if you occasionally want to update this key, it's not too bad. What we're proposing for long-term security is a megabyte, so you feel that. But then what happens with post-quantum, so I mentioned 3 papers with quantum analysis, Grover does a square root on the simplest attack and less than a square root on the more advanced attacks. So basically, similar to symmetric cryptography, we have a good handle at our current knowledge, and I mean, in this workshop, we're encouraging more people to look into this. So if you can break this, here is a nice and juicy target. This is something where at this moment I would say it's the encryption system where I have the highest trust. So where I feel like, okay, if something happened, I would be really surprised. So please, go ahead. All right, so this was the advertisement part of the system, of the talk. Let's go back to actually teaching some stuff. So I mentioned the decoding problem before. I mentioned the NP hardness result. And so there are two views on this decoding. So the normal thing is you have your code word that you're sending and some of the positions flip. So then you have what we call the decoding problem. Often enough, somebody tells you what the weight is. In our crypto systems, we will know for sure what the weight of this added code word is going to be, of this extra error is going to be. Also notations, so we talk about the Hamming weight or Hamming distance. So Hamming weight is the number of non-zero positions. Hamming distance is the number of positions where two vectors differ. So unlike lattices, our errors are discrete. So it's either there is an error or there is not an error. So we're just counting how many there are. And so then we take something which is t steps away from a code word. Well, okay, in each coordinate I can go one away. I flip from a 0 to a 1 or from a 1 to a 0. And then nice families where we can decode efficiently. I'm going to briefly show Goppa codes here, but if you're taking a course in coding theory, you're first going to see PCH codes, you're going to see Reed-Solomon codes, and then you're going to see more advanced codes. For the best attacks that we have generically that work, if we don't know anything about the code, if it's a randomly chosen matrix, if it doesn't have any structure, then we have some exponential time attacks, algorithms in this case. And then for some of those, we have structural attacks, so attacks that take into account how the code is generated and can actually see through whatever perturbations we put there. One last thing on the decoding. I mean, I showed you the parity check matrix, and so you can also see the decoding problem as a syndrome decoding. So syndrome is the output of computing h times this vector. If this x was a code word, then all parity checks are satisfied, so the syndrome is 0. If the syndrome is non-zero, we know an error has occurred. But the weight of the syndrome doesn't give us any indication of how many errors have occurred, because that's just the sum of the columns of h where we have some errors. And the columns of h can be fairly dense. So even if there's just one error, well, we see one of the columns. Remember, we saw the 101 example before. It was just one error, but it had 2/3 of the bit set. And so you can now also ask, hey, if I have a syndrome decoder, is that better or worse than having a general decoder? So syndrome decoder is something which takes this S and outputs an error vector. And the normal decoder is something which takes the erroneous vector and outputs the error. Well, those two are equivalent. I've been leaving the slide up long enough, so I hope you have started thinking about it. If you have a syndrome decoder and you have received an erroneous code word, well, you can just compute the syndrome. That's the easy direction. You take your thing, your x, you multiply by h, you're getting a syndrome, you use the syndrome decoder, you're getting your error vector, and then you add x and the error, and you're getting the fixed code word. Now, the other way around, if you only have a generic decoder, but you're only giving a syndrome, which is much shorter, you have this n minus k bits, how can you expand this to something which has the full length n? And before I was saying, hey, can we find something which maps to it? So am I asking you now to solve this allegedly hard problem, finding a pre-image of the syndrome? Okay, so first of all, I'm doing the easy case again. I assume systematic form. In this case, well, you can put the identity in whatever subpositions, doesn't matter. It's simpler to present this way. Now, if I have the identity in those positions, then it's easy to find one vector which maps to S. Namely, I'm putting zeros in the part of Q. And this is an n minus k, so that's as wide or as high as my syndrome is. And I'm putting the syndrome here. Now, this vector times h. Well, again, remember, I'm writing my things. This is a column vector in principle, so I have zeros multiplied by Q, and then S multiplied by the identity matrix. So of course I'm getting S. So this is a vector which maps to S. But this is normally not a solution to my decoding problem. Because my decoding problem says I want to find a low weight vector. I want to find something which has very few entries that are non-zero. Okay, there are lots of zeros here. I have k zeros here, but there are probably way too many non-zeros in this S. I'm having n minus k positions there, and the number of errors I'm looking for is typically much lower than a random S vector would have. I mean, it could happen that it's the right thing, but typically it's not. Okay, so Niederreiter. Already promised it would come. So Niederreiter says, let's take a code that we can nicely decode and take the parity check matrix of that. And then do some stuff, and this is where cryptanalysis has to look whether this is actually secure. We're trying to perturb this nice parity check matrix with other matrices to come out with something which looks much more generic. So this is where things can go wrong. This has gone wrong for some codes, including the one from Niederreiter's system that he originally proposed, because these steps might not hide the structure well enough. But let's be optimistic for a moment and just explain how the system works in the sense of, well, we can encrypt and decrypt, and then worry about how attacks can work. So what we do is we take our nice parity check matrix H here, and we multiply from left and right with two matrices. Now, we want to preserve the rank and so on, so these have to be invotable, but we need to have more restrictions on the one on the right here. This P has to be a permutation matrix. So a permutation matrix is a matrix which has per row exactly 1, 1, and per column exactly 1, 1. And that means it just shifts, like if you multiply a vector byte, it just shifts or permutes the positions between those. So most importantly, if you take, for instance, our error vector E and multiply it by this, it will not increase the weight. So permutation matrix just swaps around the positions, but doesn't change the weight of it. And this S is a general invotable matrix, so there we have a lot of choices. And then the public key is going to be this matrix K. So the product S times H times P, where K is giving away all the information, H is giving away all the information, and then P and S are there to protect that. To encrypt, and this is where Niederreiter is a little clunky, but just think of you sending a random message, so you don't have to worry about this encoding. He says he can only encrypt messages which have exactly weight T. So in a CAM scenario or in a hybrid encryption scenario where you're sending your AES key, what you do is you pick a random key of weight T, and then you look back, you can actually find complicated algorithms which turn a string, and you calculate how big the message space is, and you pick one of those strings and turn this into a string which has exactly that weight. But we don't have to bother with this because we don't typically care about it. Okay, so the encryption is very simple. We just take this public key, multiply by this vector, and we're getting a syndrome. Nice feature of Niederreiter, which is why I'm presenting this over MacLeese, is that the ciphertext is actually very nice and short. It is just the height of the matrix, not the length of the matrix. So what MacLeese initially had done was something where the code words were the full length, and Niederreiter had this nice idea of saying, hey, if you have the syndrome, we can do the same, and then it's just a little clunky on the encryption part, on the encoding part. And then the decryption, so what the attacker is faced with, is to find some E which has the right weight. And that typically is only 1, so find the vector that the encryption was putting in there. So if you have a passive attacker, so somebody who is not messing you, feeding you other stuff and so on, then he's faced with exactly the T-error decoding problem in the syndrome version, but we know now it's the same as the other one. Okay, it's nice that the attacker can't decode, but can we still decode? It's kind of helpful for a crypto system if we actually can get the message back. Okay, now we come to the part where it was important how we chose these pieces. So remember that K, the public key, was this general invotable matrix times H times a permutation matrix, and we're now given this thing. Now we are the legitimate recipient, so we know all the matrices in there. So we know P, we know S. So for now, I'm not wearing my tech hat, but I'm wearing my user hat. So I can just take this S and invert it because I have it. And probably I want to actually store S inverse because that's what I'm using afterwards. Okay, if I left multiply the syndrome by this, then, well, this just cancels the S here. So that's nice. And then I'm left with HPE. And I'm using that P times E. Well, P is just a permutation matrix. So P times E has the same weight as E has itself. And we have chosen a code which we can efficiently decode. And okay, we should have chosen the T so that we can efficiently decode T errors. And so we're getting PE instead of E. But P is a permutation matrix, and we know this. So at this moment, we use our efficient decoding algorithm. Here we use our secret knowledge of how to efficiently decode this code represented by H, which is hidden in the code represented by K. And then the last step, okay, we unpermute this vector, so we just multiply by P inverse, and we're getting the error vector. So then we're getting back to the error that actually the sender had put in there, and then either continue in the same hybrid way, so do the same as the sender, hash this and turn it into an AS key, or in the original Niederreiter, well, this would be the message already. Yes?
Does T have any relation with your choice of S and
Does what have any?
T?
T. Okay, so T is a system parameter, so people who work in this system, they know how long the code is, N, and K is also fixed, and T is also fixed. So everybody will choose codes in a certain family, and I haven't told you anything yet about this family. So far you could think, okay, the family is of 1, so how much secrecy is there? We're actually going to look at a family where there's a lot of choices for H for the same parameters N, K, and T. So we're going to put in those 3 things, and I'm going to show you a huge family of codes that are all equally good. But yes, you do want you're picking your code so that you can efficiently decode T errors. And if you don't have many errors, well, the job of the attacker will get harder with more errors. So if you at best can correct 5 errors, then if you're thinking of like brute force attack, you have this expanded word and you know 5 of those positions. Then, okay, you're basically picking N, choose 5, try all of them, so have an N cube attack. So T has to be sufficiently large, N has to be sufficiently large that this N to the T attack, it's less. I mean, N choose T is less than N to the T, but for small values, the best approximation, that this thing does not actually break it. So you want to have codes which have sufficiently many errors. To give you a concrete example, what McLeese had in his original paper was N being 1024, K being 524, and T being 50. So there were 50 errors added to a 1000-bit word, just for sizes. And now we're going for something 3000 for N and 100 something for the number of errors. So it's not huge. The key size really comes from, well, it's 3000 this way and 1500 that way. Okay, so codes nicely leads over to this. So what McLeese proposed was using Goppa codes, and those have been holding up very well. What then Niederreiter proposed was doing Reed-Solomon codes, and they got broken just a few years later by Shestakov and Sedelnikov, showing that there's too much structure in these codes. It's a too restricted family, and you can see in this K, in the public key, you can figure out what the code was that was put in there. So if you can find that, then it's game over. There are more corpses in the way. I mean, coding theorists, once we talk to them, going like, hey, look, can we have your nicest code? Then they come with the nicest code, and then we say, oh, that wasn't good enough. It's sometimes, I'm seeing smiles from a coding theorist over there. So it is unclear what makes a code good. But we have seen some codes which were not good, where the structure was too strong, and in the end it just means people have to look at those codes for a long time to see whether they can see anything. And nicely enough, Goppa codes were proposed in the first and have been considered for the whole time, so we're still very happy with those. But for instance, in this competition has several, it's a mouthful, quasi-cyclic medium density parity check. I'm not going to write this out on the slide, else I'm running overflow. So this appeared on a talk, well, yesterday, but it was a different workshop. So you have E. Parity check matrix is H, which has medium density, and then you have other decoding algorithms. And quasi-cyclic means that your code doesn't need the full two-dimensional thing to be represented, but you have E structure where the first row with its cyclic shifts tells you the parts under it. And then quasi-cyclic means there's this part with the shifts, there's this part with the shifts, and there can be a third part if you want. Also, rank metric codes are in this competition. I've seen a talk about it at a Decoding workshop, and I was very happy that now the paper is announced, but I still couldn't find it. So I don't know whether this has gotten worse or better. I mean, the attack got worse. So I'm writing some scratches because I haven't seen it, but this paper will be at Eurocrypt. So there is some progress on a different type of codes. I'm just talking about linear codes with Hamming metric, and there is something else called rank metric codes in this competition, and they have gotten a little bit of a hit. All right, so security notions. So what we want to achieve is a one-way encryption system. The systems are presented so far as that schoolbook version. So these are not CCA secure, so you do want to throw on it some transform for encryption, or, well, you probably want to go for a CAMDEM version. So don't bother with the encoding. So what we typically do is we pick for Niederreiter a random E of the right weight, then use the hash of this for AES, and we also make sure to authenticate, and then we toss some Fujisaku on it, or some re-encryption. So things to make sure that nobody can send us slightly wrong code words. Because if somebody has the power to send you code words and see how you react, they could figure out whether it's the right distance away and basically combinatorially extract from you, is this a position with an error or not? So if you don't put the transforms on there, there are lots of active attacks that, well, it's not good. Then there's a kind of, the tautological result is if you can break the one-wayness, you can either distinguish the key from random, and that's why I'm, Tanja, coming back to your question from before. I know that the result here is from random, and so I need to look which reduction they're using, which NP hardness statement they're doing there, because it says from random and not from the worst case, because that would be kind of a bad one. And then what we normally look for is, can we actually break one-wayness for a particular given key? And then our attacks, we distinguish into two categories. We have the generic attacks, and that's what I'm going to speak about in the next few minutes. So that's information set decoding. So those attacks work for any code. They work for the ugly case of K that we hope we are presenting our attacker with. But then there's also structural attacks. Those are attacks which are trying to find what code have I put in there? What nice decoding algorithm am I hiding in my K? So this is where, on the previous slide, I was saying we have these corpses. So for instance, there was these gabidular codes, which had a very nice structure with not binary codes, but like subfields. So you had a FP and you had a FP to the N, and you could basically figure out how the Frobenius would be acting on pieces. And you could still see this on the K level, even though it was totally messing up the field structure. You could piece together which are kind of the pieces in the subfields and the extension fields. For such special decoding attacks, so their Gröbner bases have been shown to be quite efficient. Now, of course, you might think, hey, Gröbner bases is quite a big hammer, but if you're trying to find the structure, there were some where this helped. So it was not as like Gröbner bases with full size N. And then for the generic attacks, well, let me flip to the next slide for that. Oh yeah, sure.
Isn't it the case of like an algebra that we need many equations and we don't have that many?
For Gröbner bases, you mean?
Yeah, for the computation of Gröbner bases to succeed.
Okay, so that depends on how you want to use a Gröbner basis attack. I'm thinking of the algebraic geometry attacks, for instance, that you could use Gröbner bases there. I'm really thinking structural attacks where you're having a family of codes in there. For instance, you're having like elliptic curve codes or Hermitian codes.
No, I was more like just generic code. The same way as we attack the Lee. We could also do the base and construct equations from samples.
Yeah.
But the problem is that we don't have enough samples. And I guess the same problem is here, no?
Can't think of any of the papers that is trying that. And I also, I mean, you would have to, I mean, not having enough equation, you can always think of bootstrapping. So that per se is not.
Yes, because I'm not a block too.
Yeah, but here, yeah, they cancel out. So maybe that's, yeah. So I was thinking of Goppa bases really just for structural attacks, because I haven't seen it anywhere for generic. Okay, so I was hinting before, like, how would you do a brute force attack? I was giving you this example with the n positions and just n length and 5 positions. So in general, if I tell you, hey, t of the positions are in error, then you would say, well, you're picking randomly t columns of this, see whether those add up to the syndrome you've received. If yes, you win. If no, well, try the next. There are lots of those. There are, as I said, n choose t such columns. So you can say, okay, it's n choose t full matrix computations, each time taking, well, the sum, or you can do this like basically swap in, swap out, swap in, swap out. So you can bring it down to most of the time that's the cost of 1 extra addition. But that's still a lot. So we're here trying to figure out the positions, but at the same time, when you think about it, when we're trying to figure out a position, we're also trying to figure out the non-positions. So we're kind of fixing both of those. And the Prange attack is better in that it says, hey, let's just figure out some non-positions. So Prange, the original information set decoding attack, is saying, let's go for easy setup. Let's assume there is no error over here and only errors over here. Well, then we can very easily read off what our syndrome should be. It should be just this, plus this, plus this, plus this. So if our syndrome has just weight t, then we're done in the same way that I said before. We can turn a syndrome decoder, a syndrome decoding problem into a generic decoding problem by, well, expanding the vector with zeros. But normally, our syndrome doesn't have weight t. And normally, we don't have our matrix or our arrangement so that all errors are over here and none of the errors are over here. But what Prange observed is, hey, we can do this. We can randomly swap around columns. The same way that in the brute force attack, you're picking columns. Well, that's the same as moving columns left and right. And so what he's doing is we're permuting k, meaning we're permuting these positions. And yes, there's a ton of positions. If you're picking the left side or the right side, well, it's always n minus k or k of those. And then you do systematic form. If that fails, try again. If it doesn't fail, then stuff here, we will win if all the errors are over here and none of the errors is over here. So we can find out from the new syndrome whether we have succeeded. Now, how do we update our syndrome? How do we get into the syndrome that matches this thing on the permuted matrix? Well, what we've done with the steps is we've applied basically 2 matrices. We have done a permutation, that was the initial thing, swapping things left and right. And we've applied an invertible matrix U in the Gaussian elimination when we got to systematic form. Okay, so if that's our K prime, then our S prime has to go through the same transformations. Well, the P doesn't apply to S, but the U would apply to S as well. So we're updating S to U times S. And if we are correct that all the errors are over here and none of the errors is over here, then this U times S will have the right weight. If that's correct, then we know what the vector looks like. Then we have found an E prime which fits this. And then we need to unpermute in order to get the positions in the right places. So this is the mother of all information set decoding attacks. So let me spend a moment longer on going through this. Instead of in the brute force where we're figuring out, we're forcing all the positions of the errors and all the positions of the non-errors, here we're having a much better chance because we're only saying, well, it's a left-right split. But we're leaving the error a lot of range here. We're only restricting the error to being somewhere in these n minus k positions. But we don't have to fix it. We don't have to be exactly right. So the cost of this thing, when do we succeed? Well, we succeed if the permutation gets us such that of all the n choose t different positions that we can have, we have restricted the error to just n minus k over t. So how many times do you have to repeat this? That means we win in the case that we have n minus k over t, so if the errors are over here, out of all the positions, out of n choose t. Now this is a very simple algorithm, and simple algorithm is nice in this case because we can also see how to turn this into a quantum attack. We're looking for something which gives the right weight. I mean, you have to do turn of this into a computational, into a circuit and so on, but you're basically getting a square root on the whole thing. Leaving out constants here, the constants do include something for the probability that this thing can actually be put into a systematic form, so only about a third of all matrices work, so you have another constant sitting around there. But O of something just gives you a square root speed up. I mean, the constants are the same in both classical and quantum. The 0.29. Then one more attack, which I'm going to go through in detail to show how things get more complicated, but then we also need more storage, is Lee-Brickell, who said, okay, we're doing the same as Prange. Again, we're doing this permutation thing, systematic form, updating our S, that's the same like the permutation, the U, we're applying this to here. And then we turn this into a search problem by saying, well, we allow a few of the errors on that side. There we need to do a brute force search. But our probability will get better because we're allowing, say, 2 errors over here, and then all but 2 errors over here. Now our check gets more expensive. We need to check through all the positions on the left, and then check whether, well, for those positions, this thing here has the right weight, namely, well, in this case, 2, or in general, p of those can be off. And then, well, we unpermute whatever comes around. So what is the cost now? So we now have the improvement factor here that we don't have to have all the p here. So we're having a k choose p for the p positions on the left, and we have a t choose t minus n minus k choose t minus p on the right. So this is bigger, so the cost goes down compared to before. But we also have the brute force search over on this part where we're trying to combine all the combinations and check them. Okay, and then comes a whole bunch more attacks where you're improving where you're looking, like you don't look on all positions and so on. Once you're here, then you have to figure out where do you apply your Grover and how do you handle Grover with storage. You can do it. So the improvements then are normally assume that you have storage sitting around because you're trying to find something that maps to a certain target on there. So then Leon is saying, hey, we can make this cheaper by only checking on certain positions. Stern is turning this into a collision search problem on here. And then further papers are improving in here that you don't have to go all the way down, or that you can skip some part here. So at the moment we are having some regions where you're not allowed to have any errors. These green lines won't be allowed to have errors, which gets too restrictive for large parameters. So these then have quantum speedups which are less than square root of the whole thing. I promised you to show briefly how these codes are chosen to convince you that there are many of them. So very quick one slide thing, what is a binary Goppa code? Okay, so the freedom that we have is as follows. We're picking a power of 2. Well, there's a parameter m which comes in, and then we, over this bigger field, over f2 to the m, we're picking a polynomial which must be square free. We typically choose it to be irreducible even, definitely guaranteed to be square free. And this polynomial has degree t. So this is the same t that we're going to use later on as the number of errors. So we can totally figure out how many errors we want to compute, how many errors we want to add or be able to correct by having this parameter t. Now, t must not be 0 for any of the positions in this larger field, well, actually just in this list. But if you pick your polynomial to be irreducible, then you're very sure it doesn't have any roots. So that's a very simple thing. This list here will be different elements of the finite field f2 to the m. So the length is bounded by the number of elements in there. And okay, our attack will get more expensive the larger n is. So okay, your m has to be sufficiently large. So typically what you're seeing is powers of 2 running around. And then this is either the full thing or a subset of it. This is called the support of the code. And then that's the code. Isn't it beautiful? Okay. You can look that this is actually linear by saying, well, if you add 2 of those code words, meaning 2 of those things satisfy the same equation, then also their sum will satisfy it, because, well, it's linear in the pieces. So, yep, it is a code. It's not the normal description they're used to. It doesn't give you a big parity check matrix. It doesn't give you a generator matrix. Of course, you can recover a parity check matrix from this thing. It's not a hard problem. The dimension typically, if everything is full rank and so on, so there's a bound, but typically we're seeing full rank in our examples. So n minus m times t is this k. And the distance is 2t plus 1. So that's the same error. That should be a d. The distance d is larger than 2t plus 1. That would be otherwise rather strange. Okay, so there are many of those codes. I can pick any polynomial of degree t, even if I just restrict to irreducible, and then I can also rearrange the support. Now, the last part doesn't give much information, but it still gives me, well, I mean, if I have a fixed ordering in mind, I can test it. This I showed you before about how these codes belong together. A nice thing about Goppa codes is that I can actually skip most of these things by saying, oh, the permutation is just the different rearrangements of the different field elements. So I don't actually need to pick a P extra. It is already in my choice of code. So I don't have to remember this big matrix P. It's just a different ordering of the field elements that I have to remember. And then turning something into systematic form implicitly gives you a matrix. So you also don't need to remember it. So you don't actually need any of the P and S stuff that I showed for random codes or general case. For Goppa codes, all you need to remember is which ordering of the field elements did you have and what polynomial did you pick. And then you have a nice, efficient decoding algorithm to Burger Massey, which does that. Sandré has an attack paper on support splitting. So if you want to figure out whether the code that you have found is actually the correct code, then that part is efficient, at least for all observed cases. It runs in polynomial time. There are some, I mean, not for every code it must, but at least for Goppa codes it's believed, and there are some good indications that it always will be. So support splitting says it computes code equivalents for Goppa codes. So you're giving a candidate Goppa code and the public key, and then the support splitting algorithm efficiently answers saying, is this the same or not? However, there are a ton of Goppa codes. So even if you have an efficient test for this, you run it exponentially many times. And so this part is not the hard part. The number of codes is sufficient. And then that's it for me to say. I have one last slide with advertisement. Thank you for your attention.
I'm sure we have time for questions. Maybe at this most one.
Martin is asking.
In lattice-land, we have this polynomial memory, super exponential time, and exponential memory, exponential time. Is there anything like how's the layer of the Lange code? Like at least it seems like all these algorithms are exponential time, but polynomial memory.
No, Stern you can. So Stern and follow-up algorithms, including some with RxMy, those use a lot of memory as well. So on the left part.
So there's this distinction. Like
yeah.
I'm asking if there's a world separation for codes in a similar way as it seems to appear for lattices.
So I mean, what I skipped is all the tuning of parameters. You're typically expecting some exponential also in the storage. And so, I mean, when we did the attack, it was in the exponential land, but small enough to fit. So you tune your parameters to fit this. On the theory side, I'm not aware of the separation.